So the next bit of property of matter we need to talk about a device known as cloud chamber. The cloud chamber was originally developed to explore clouds. When we talk about the atmosphere, what actually produces clouds, well, we know it's condensation in the atmosphere. But why does it condense? I don't remember the name of the gentleman, but meteorologist who wants to explore how clouds are being formed, I think in Iceland or a northern region of the world. So he develops a device which can saturate the air inside of the chamber to the point where it's just about ready to form a cloud. And then you can introduce small disturbance. And once that disturbance happens, you can see the formation of clouds. Okay? It's a relatively small device. I think it's no bigger than maybe a modern-day pressure cooker. But the idea is that he develops it so you can study clouds. But the key principle, the key property of the cloud chamber is if a disruption is introduced into the cloud chamber then condenses along that disruption. And you get precipitants. Thank you. Precipitants in the cloud chamber. Okay? Where it really comes into being, when it really comes into its existence, is in particle collision or stuff like that. So, what we do is we'll fire a particle, more than likely it's going to be a proton. We'll fire another particle like that, maybe another proton, maybe it's a neutron and a neutron. Okay? And those particles are going to be fired towards each other inside this cloud chamber. Well, that proton is creating precipitants on the bottom of the cloud chamber, which is nothing more than like a photographic piece of paper, where if you get something to hit it, it starts developing. Okay, same on this side. So you're getting drops forming below the path of the protons. Well, when those protons collide, they explode. It destroys the protons and they explode, and particles are ejected from that proton. Cool? In all sorts of directions. So they collide, they explode, and particles start to be formed at that collision. Well, if you expose it to a magnetic field, and expose this cloud chamber to a magnetic field, we can keep track of things like the mass value, the mass to charge ratio of particles that are being formed when these protons are colliding. Okay? So looking at it from above instead of from the sides, you end up getting the diagram with something like this. And you've all seen these. You can go online and type in the word cloud chamber, and you'll see these, where you have your incoming proton colliding with another proton, which bends slightly because they're exposed to a magnetic field. They have motion with tensile Lorentz force. And then you get an explosion in the center, and you get particles that end up doing something like this, and then some like this, and some that go off like this, and you get all this general motion coming out of it. Okay? Some of them are intense, they're beautiful, they've added color to them, so it's really, really cool. Okay? And then you get a weird phenomenon that does this, and then it picks up sometimes like that. Okay? So you get all of this happening inside that cloud chamber. And this is from a top-down look. There's a bang, explosion. All these particles come flying out in all sorts of different paths and stuff like that. Okay? All of it's just coming out of that one collision. Well, what we can do with that information is that we can determine things like charge to mass ratio. If this thing is moving in a circular path, and I know the strength of the magnetic field, I know the charge to mass ratio. And this particle, and even these particles, which have slides down to them, I can pick up all that information. Okay? Well, the greater the curvature, the lower the mass value. So my protons are going to have less curvature. The electrons that are being formed are going to have less curvature. Where other things with less mass than electrons are going to have much smaller curvature. Okay? Or much larger, or much smaller curvature. Okay? So, in order to describe what's going on in the cloud chamber, a gentleman by the name of Feynman comes up with what's called the Feynman diagram. Okay? And all I'm going to show you is an example using an electron and a photon. So, in a Feynman diagram, you have a particle like an electron with relatively high mass value, so very little curvature. And basically, we can say it's a straight line. Okay? In that diagram, here's my straight line. So I know it's either an electron or a proton, but I actually know it's an electron. And let's say that particle ends up going like this sometime later. So the path of that electron would look something like that. Okay? The Feynman diagram would suggest that something happened to that particle, and it's something that doesn't have mass value. So something that doesn't have mass intersected this particle and changed its motion. Okay? Because if it had mass, there would be a line in my cloud chamber. Okay? That would show that a massive object collided with this object, forcing its direction to change. But because in the cloud chamber there's no lines leading to that, we can say one of two things. We can say that this thing generated an electron, or generated a photon, or was intersected with a photon. Okay? So if the net momentum is in this direction, and this object picked up momentum in that direction, okay? It's picked up momentum to go in this direction. That means that you have to have a photon throw it off in another direction, in the opposite direction, at that instant. So that photon is either going to be in this direction, which gives me the conservation of momentum, it still holds true. The momentum of this and the momentum of this have to equal this momentum. Or more importantly, the momentum in this direction has to equal the momentum in this direction. Okay? So the momentum in this direction has to equal the momentum in that direction. But this is a Feynman diagram. It says, oh, look, I have particle motion inside of a cloud chamber. That particle then changes its direction. And because of that change direction, I know it ejected an electron. Okay? Cool? And I can determine the direction of that electron. I can even determine or not the electron, but the photon. Determine both the momentum value of it, which then will give me the frequency value of it, by exploring the angle in which this electron changes its direction. Okay? Cool? So that's a real brief rundown of the Feynman diagrams for an electron and photon interaction. Actually, you do end up getting some weird phenomena like this. And what ends up happening is this degrades into a photon, intersects another photon, and then creates an electron. So you have electron to photon intersecting with another photon back to an electron. Okay? So there's all sorts of weird things that can be done with the Feynman diagram. Actually, if you go online and you look up Feynman diagrams and you look up penguin, there's a drawing of an intersection of several particles that end up looking like a penguin. It was a dare. It's like, go ahead, see if you can make your Feynman diagram look like the creature on the planet. Okay? But the other thing that does come out of these colliders, and why we continue to explore and spend billions of dollars on colliders, are particles that do this. Okay? These small little swirls that we're getting are not associated with our fundamental particles, our protons, neutrons, and electrons. Their mass values are much smaller than that. So in these collisions, we start developing an idea of what is matter. At least another step to describe what is matter. So these particles, we believe, are what we call quarks. Now, the word quark comes from a piece of literature, and I don't remember the book, so you're going to have to look that up online. Okay? So these quarks are being formed in the collision and bonding and creating other particles that have different mass values, smaller mass values, than the particles that are involved in the collision. Okay? So quarks, we believe, make up protons and neutrons and a whole series of other particles. Okay? And these particles that are composed of quarks are what's called as hadrons. Okay? So when we talk about hadrons, it's H-Y-dron. I think that's right. hadrons are anything that's composed of quarks. We also have what's called a lepton. And leptons are anything that are not composed of quarks. Leptons are electrons or neutrinos. It doesn't seem like an electron is composed of quarks, where our heavier particles like a neutron and a proton are composed of quarks. We call those hadrons. Or, I think in barons, and then there's a pentahadron, and then leptons are just leptons. And then you have your categories like electron, neutrino, that sort of stuff, also in that lepton category. Hadron, baron, I think it's a baron, and a pentahadron. Okay, cool. Now what makes a hadron is a composition of 3 quarks. Okay, 3 quarks make up a hadron. Okay? So 3 quarks make up a hadron. Let's talk about how those 3 quarks make up a hadron in the next video.